Welcome back to Science with Sleepy, where curiosity stretches across time as gently as the Milky Way stretches across the night sky. And tonight our journey runs long and unhurried, giving you plenty of time to drift off while your mind wanders among the stars. Picture yourself lying on a quiet hillside thousands of years ago. No phones, no streetlights, no cars, just the sound of insects and the soft rustle of wind in the grass. Above you, the sky is not just decoration. It is your calendar, your clock, your compass, and your storybook, all at once. Every bright point matters, and the people around you have spent generations learning what each one means. Tonight we are going to travel into that world. We will visit ancient Mesopotamia, where priests watched the rising of stars to time their rituals. We will stand among the stones of ancient Egypt, where the layout of temples lined up with the sky. We will look from Greek islands where sailors steered by constellations, and from Andean mountaintops and Polynesian canoes where the night was a living map. All of this happened without telescopes, without cameras, and without even glass lenses. So how did they do it? As we drift together through this long, gentle story, we will see how simple tools like sticks, strings, and shadows turned into precise instruments. We will see how careful watching over many lifetimes became the first star catalogs. And we will see how myths and gods and animals drawn across the sky were not just stories, but memory systems that helped people remember where everything was. By the time we reach the end, you will know how humans mapped the sky using nothing more than patient eyes and clever ideas. So let your shoulders relax and your jaw unclench. If you like falling asleep to slow science and deep questions, and if these long journeys help you end your day more gently, you can always subscribe, so you can find your way back here the next time you need a calm night. For now, you do not have to remember any of the names or dates. You can just listen as we walk slowly through the ancient night and ask a simple question. How did people, long before telescopes, turn the sky into a map? Chapter 1. A world without streetlights. To understand how ancient people mapped the stars, we first need to imagine their sky. Today, many of us live under a washed-out dome of gray-orange light. In big cities, only a handful of bright stars are visible. But for most of human history, the night sky was astonishingly rich. On a clear, moonless night, far from any artificial light, your eyes can adapt so well that you can see the soft band of the Milky Way, star clouds, dark dust lanes, and thousands of individual stars all at once. Astronomers today estimate that a person with good eyesight, in a truly dark place, can see about 500 to 3,000 stars at any one time. Over the course of the year, as Earth moves around the Sun and different parts of the sky come into view, a single observer can see close to half of all the stars in the sky with the naked eye. That is tens of thousands of points of light, each in a fixed position relative to its neighbors. To ancient people, this was not noise, it was structure. Studies by the International Dark Sky Association have measured sky brightness in remote locations, and found that truly dark skies are becoming increasingly rare. In the darkest places on Earth, the sky can be up to 200 times darker than in typical suburban areas. This means ancient observers would have seen many more stars than most people can see today, even in rural areas. The difference is not just in the number of visible stars, but also in the clarity of the Milky Way, which would have appeared as a bright, structured band, rather than a faint smudge. This rich star field would have made pattern recognition much easier for ancient skywatchers. Even without telescopes, the human eye is a very capable instrument. Experiments in vision science show that people can detect differences in position as small as a few arc minutes under good conditions. An arcminute is 1/60th of a degree. For comparison, your little finger at arm's length covers about 1 degree of sky, so a careful observer who trains their eyes night after night can notice very small shifts in where objects appear. This is more than enough precision to notice if a bright star rises slightly north or south along the horizon, or if a planet is out of place. Modern astronomers sometimes test naked eye precision by asking volunteers to point out when a bright star touches a marked line, or when two stars look perfectly aligned. Again and again, the results show that the human eye and brain together can notice surprisingly tiny changes in angle, especially when you can compare one night to the next. This same quiet skill was at work thousands of years ago on rooftops and hilltops all over the world. The ability to see fine details in the dark improves dramatically when you give your eyes time to adjust. This process, called dark adaptation, takes about 20 to 30 minutes in complete darkness. During this time, your pupils widen to let in more light, and special cells in your retina called rods become more sensitive. Ancient skywatchers who spent hours outside at night would have had eyes far more adapted to darkness than most of us do today. They could see stars that we might miss, and they could notice subtle differences in brightness that helped them distinguish one star from another. Color vision also changes in dim light. The cone cells that detect color need bright light to work well. In darkness, your eyes rely more on rod cells, which are better at detecting faint light, but cannot distinguish colors. This is why stars appear white or slightly bluish to the naked eye, even though telescopes reveal they come in many colors. Ancient observers would have noticed that some stars look slightly different in brightness or hue, even if they could not name the colors. These subtle differences helped them remember and identify specific stars. Some ancient cultures did notice and name star colors, even with naked eye observations. The Chinese, for example, described certain stars as having a reddish or yellowish tint. The star Antares, which means rival of Mars in Greek, was named because of its reddish appearance, similar to the planet Mars. Betelgeuse, the bright red supergiant in Orion, was also noted for its color by many cultures. These color distinctions, subtle though they were, became part of the star lore that helped people remember and identify specific stars in the vast night sky. The ability to see faint stars also improves when you look slightly away from them rather than directly at them. This is because the most sensitive part of your retina, the fovea, is packed with cone cells that need bright light. The areas around the fovea have more rod cells, which are better at detecting dim light. Ancient skywatchers likely discovered this trick naturally, learning to use their peripheral vision to spot faint stars, or to see the Milky Way more clearly. This technique, called averted vision, is still used by modern amateur astronomers. Researchers studying vision science have found that experienced observers can detect stars up to 2 magnitudes fainter using averted vision, compared to direct vision. This means they can see stars that are about 6 times dimmer. For ancient skywatchers who spent hours outside at night, this natural technique would have significantly expanded the number of stars they could observe and map. The Milky Way, which appears as a faint band to most people, would have been much more detailed and structured to observers using these techniques regularly. Ancient skywatchers did not just look once and walk away. They watched every clear night for years, and they taught their children to do the same. Stories from indigenous cultures around the world describe older community members pointing out the patterns of the sky to younger ones. Anthropologists who work with traditional navigators in the Pacific, for example, report that children begin learning the names and paths of stars from a very young age, long before they ever sail alone. Something similar likely happened in Mesopotamia, in Egypt, in China, and in many other regions. In Australia, Aboriginal elders have passed down star stories for thousands of years. Astronomers and anthropologists who listen to these stories have noticed that some of them encode very specific observations. For example, the emu in the sky is a dark shape, made not from bright stars, but from dark dust lanes in the Milky Way. Its rising and position in the sky match the breeding season of real emus on the ground. When this dark emu stands upright in the sky, it is time to look for emu eggs. The sky pattern and the animal behavior are locked together in memory. Other Aboriginal star stories describe the Seven Sisters, a cluster we call the Pleiades, and link their appearance to seasonal changes. In some traditions, when the Seven Sisters disappear from the evening sky in late autumn, it signals the start of the cold season. When they return in spring, warmer weather follows. These connections between sky events and earthly seasons were not just poetic. They were practical guides for when to hunt, when to gather certain plants, and when to move to different areas. The Aboriginal approach to mapping the sky often used the landscape itself as a reference. A particular star might be remembered as rising over a specific mountain or tree. The relationship between the land and the sky created a three-dimensional map that helped people navigate both physically and temporally. This integration of sky knowledge with place knowledge created a rich, layered understanding of the world that modern astronomy, for all its precision, sometimes misses. In some Aboriginal traditions, the sky is not just a map, but a mirror of the land. The patterns of stars reflect the patterns of the landscape, creating a unified cosmology where the earth and sky are part of one continuous story. This perspective helped people remember star positions by linking them to familiar landmarks. When traveling, they could use the sky to find their way, but they could also use the land to remember the sky. This bi-directional relationship created a navigation system that was both practical and deeply meaningful. The stories told about stars in Aboriginal cultures often encode complex astronomical knowledge. For example, some stories describe the relative motions of stars, how they move across the sky over the course of a night or a year. These narratives helped preserve observational knowledge across generations, turning abstract patterns into memorable tales. When an elder told a story about how the Seven Sisters chased a man across the sky, they were also teaching about the seasonal motion of the Pleiades and their relationship to other stars. The story made the astronomy memorable, and the astronomy made the story meaningful. Anthropologists working with Aboriginal communities have documented star stories that accurately describe astronomical events occurring over thousands of years. Some stories mention features that are no longer visible due to precession, Earth's slow wobble. This suggests these narratives have been passed down for at least several thousand years, preserving astronomical knowledge across an incredible span of time. The accuracy of these stories, when compared to modern astronomical data, demonstrates how effectively oral tradition can preserve complex information when it is embedded in memorable narratives. Dr. Dwayne Hummucker, an astronomer who studies indigenous star knowledge, has found that some Aboriginal stories describe the positions of stars as they would have appeared over 7,000 years ago. These stories have been passed down through oral tradition with remarkable accuracy, preserving not just the patterns but also their relationships to seasonal events. This level of preservation over such a long period shows how important sky knowledge was to these cultures, and how effective their methods of teaching and remembering were. The stories were not just entertainment, but essential survival knowledge, which may explain why they were preserved so carefully. At first, as watching did not look like science in the modern sense, it looked like survival. The sky told you when floods would come, when the rainy season would start, when to plant seeds, and when animals would migrate. It helped you find your way across deserts or seas where there were no road signs. so people paid attention not because they were curious about galaxies, but because their lives depended on it. Over time, patterns emerged. Certain bright stars always rose just before dawn at certain times of year. Some constellations were winter patterns, others were summer patterns. The sun did not rise at the same spot on the horizon every day. It wandered back and forth over the year. The moon did not follow the same path as the stars either. It drifted among them. The planets wandered more strangely still. All of these motions were visible to the naked eye. The question was how to measure them. In the beginning, the measurement tools were the human body and the landscape itself. Your held-out hand could measure angles. A fist at arm's length is about 10 degrees across. 3 middle fingers might be about 5 degrees. One outstretched finger is about 1 degree. By stacking these rough units across the sky, early observers could estimate how far apart stars were. They did not talk in degrees and arc minutes, but they knew that this star was about 3 fists away from that one, or that a certain constellation spanned 2 hands across the southern sky. The horizon was another crucial tool. The place where Earth and sky seemed to meet was a perfect reference line. If you watched carefully, you could note exactly where a bright star first appeared or disappeared. You might line it up with a hill, a tree, or a carved post. Many cultures built special markers into the landscape for this reason. Archaeologists studying ancient sites have found repeated examples where stones or walls line up with the rising or setting points of important stars or of the sun at solstice. In the Andean highlands, for example, researchers have found carved rock pillars that align with the rising positions of the Pleiades star cluster. When these stars first appeared before dawn, they signaled the coming rainy season and helped farmers decide when to plant. In the Pacific Northwest of North America, oral traditions describe how people watched the heliacal rising of certain stars, the first appearance just before sunrise after weeks of being lost in the sun's glare, as markers for seasonal salmon runs and other events. With no electric light, these signals stood out sharply. On a dry, clear night, the difference between a regular star field and the sudden return of a bright seasonal star would be obvious, like the moment the first firefly appears in a dark field. Once people knew that this returning star always came just before a flood, or just before the hot winds, they began to treat its appearance as a cosmic announcement. Over many generations, these repeatable patterns formed the backbone of early star maps, even if those maps lived mostly in memory and stories rather than on paper. The heliacal rising of a star happens when it first becomes visible in the morning sky, just before sunrise, after being hidden in the sun's glare for weeks. This moment is not instant. It takes several days for a star to rise far enough before dawn to be clearly visible. Ancient observers would watch for this gradual return, noting the exact day when the star first appeared. This precision mattered, because a difference of just a few days could mean the difference between planting too early or too late. Different stars have different heliacal rising dates depending on their position in the sky and their brightness. Bright stars like Sirius become visible earlier in their cycle than dimmer stars. Ancient skywatchers learned to recognize these patterns, creating a calendar based not on abstract days, but on the actual appearance of specific stars. This method was more reliable than trying to count days, especially in cultures that did not have written calendars, or where calendars could drift out of sync with the seasons. The heliacal rising calendar has an advantage over fixed calendars. It automatically adjusts for the actual seasons. If the weather is unusually warm or cold, the stars still rise at the same time relative to the sun, so the calendar remains accurate. This made star-based calendars particularly useful for agricultural societies, where timing was critical. A farmer might not know the exact date, but they would know that when a certain star first appeared in the dawn sky, it was time to plant a particular crop. This direct connection between sky events and earthly needs made star calendars both practical and reliable. Some cultures developed elaborate systems using multiple stars for different purposes. One star might mark the beginning of the planting season, another the start of the rainy season, another the time to harvest. By watching a sequence of heliacal risings throughout the year, people could track the agricultural calendar with precision. This system required careful observation over many years to establish which stars rose when, but once the pattern was known, it could be passed down through generations as a reliable guide for when to perform essential tasks. Archaeologists studying ancient agricultural sites have found evidence that star-based calendars were remarkably accurate. At sites in the Andes, researchers have discovered that planting times determined by star observations matched optimal growing conditions within just a few days. This precision mattered because planting too early or too late could mean crop failure. The fact that star calendars could achieve this level of accuracy shows how carefully ancient observers must have watched the sky, and how effectively they passed down their knowledge. Modern farmers with weather forecasts and soil sensors achieve similar timing, but ancient farmers did it by reading the stars. However, some researchers caution that we should not assume all star-based calendars were equally precise. Dr. Anthony Aveni, an archaeoastronomer, notes that while some cultures developed highly accurate systems, others may have used star observations more loosely, combining them with other signs like weather patterns or animal behavior. The most successful systems likely integrated multiple sources of information, using stars as one important indicator among several. This nuanced view reminds us that ancient astronomy was practical and adaptable, not rigidly fixed to a single method. So before any stone circles, before any written tables of positions, the ancient sky was already a kind of shared map. The lines were drawn by habit, and by habit of mind. This star means plant soon. That cluster means rains are close. The long curve of the Milky Way might be remembered as a great river, or a path of migrating animals. These images were not decorations. They were memory aids, helping people keep track of where everything was, and when everything would happen. In the next chapter, we will walk into the first great stone observatories and temple alignments, where those mental maps were anchored into rock. But for now, you can imagine yourself lying on that hillside in the deep past, watching the same sky we see today, feeling it slowly turn, and knowing that every tiny point has a place and a purpose. Chapter 2: Stones that point to the sky. Now imagine that hillside again, but this time people have begun to leave marks, a row of stones on the ridge, a post planted in the ground, a notch carved into a rock where the horizon dips. Each of these is a memory anchor, a way to freeze a moment in the moving sky, so that anyone can see it, not just the person who first noticed it. Archaeologists who study ancient sites sometimes talk about archaeoastronomy, the careful study of how buildings and monuments line up with the heavens. They do not just guess. They measure angles, they simulate the sky as it would have looked thousands of years ago, and they compare those alignments with known events like solstices, equinoxes, and bright star risings. Again and again, across different continents and cultures, they find the same quiet pattern. Stones and walls are not placed randomly. They point. In ancient Mesopotamia, between the Tigris and Euphrates rivers, temple tops called ziggurats rose above the flat plains. These stepped towers gave priests a clearer view of the horizon and the stars. Clay tablets from the city of Babylon, dated to more than 200–500 years ago, record careful observations of the sky. On some of these tablets, scribes wrote down when particular stars or planets rose just before sunrise, or when the moon passed in front of a bright star. These were not casual notes. They were part of a long record that stretched over centuries. One famous set of texts is called the Mul Apin Tablets. They list constellations visible at different times of year, rising at different points along the horizon. They also describe 3 bands across the sky that correspond roughly to the paths followed by the moon and planets. Mesopotamian astronomer priests used these records to predict eclipses and to time festivals. To us, it looks like early science. To them, it was also a way of listening to what they believed were messages from the gods written in light. The Mul Apin tablets are remarkable for their systematic approach. They divide the sky into 3 paths: the path of Anu in the north, the path of Enlil in the middle, and the path of Ea in the south. These paths correspond roughly to different declination bands, regions of the sky at different distances from the celestial equator. Stars in the path of Anu never set below the horizon for observers in Mesopotamia. Stars in the path of Ea never rise above the horizon. The path of Enlil contains stars that rise and set daily. This 3-path system helped Babylonian astronomers organize the sky and predict where objects would appear. The tablets also list specific stars and constellations with their rising dates and their positions relative to each other. For example, they describe how the constellation we call Orion rises in the east when another constellation sets in the west. These relationships created a network of connections that helped observers remember and predict star positions. The system was so effective that it influenced later Greek and Islamic astronomy, forming a foundation that lasted for thousands of years. The Babylonian star lists also included information about the brightness of stars, using terms that roughly correspond to what we now call magnitude. The brightest stars were described as great or brilliant, while dimmer ones were small or faint. This classification system helped observers identify stars and remember their positions. A great star would be easier to spot and use as a reference point, while small stars might be used for more detailed navigation or timing. The Mul Apin tablets also describe the zodiac, though not in the same way we think of it today. They list constellations along the path where the sun, moon, and planets travel, creating a band across the sky. This band was divided into segments, each associated with specific stars and constellations. The concept of the zodiac as a reference frame for tracking planetary motion was one of the most important contributions of Babylonian astronomy, providing a coordinate system that made it easier to predict where planets would appear and when they would be visible. Scholars who have studied the Mul Apin tablets estimate they were compiled around 1000 BCE, but they likely contain observations dating back much earlier. The tablets list 17 or 18 constellations along the zodiac path, compared to the 12 we recognize today. This difference shows how the zodiac evolved over time, with some constellations being combined or redefined. The Babylonian system was practical rather than symbolic, designed to help observers track where planets would appear, not to predict personality traits. This focus on observation and prediction rather than interpretation made Babylonian astronomy a foundation for later scientific developments. Recent analysis of the Mul Apin tablets by Assyriologist Drive John Steele has revealed that the star lists were not just simple catalogues but sophisticated reference systems. The tablets organize stars by their rising times, their positions relative to each other, and their relationships to seasonal events. This organization made it easier for observers to find specific stars and to understand their motions. The system was so effective that it influenced astronomy for over 1,000 years, with later Greek and Islamic astronomers building on Babylonian foundations. The tablets represent one of the earliest attempts to create a systematic, written record of astronomical knowledge. Further west, along the Nile River in ancient Egypt, the sky and the land were woven even more tightly together. Every year, the Nile flooded its banks, spreading dark, fertile silt across the fields. The timing of this flood was life or death for farmers. Egyptian priests noticed that just before the flood, a bright star that had been invisible for weeks suddenly reappeared in the dawn sky. We call that star Sirius. They called it Sopdet. The first dawn rising of Sirius, called its heliacal rising, became a key marker in the Egyptian calendar. In inscriptions, the rising of Sirius is linked with the goddess Isis and with the rebirth of the land. Some temple walls and corridors are aligned so that on certain days, the rising sun, or a particular star, shines down a dark passageway and lights up a hidden chamber. At the Temple of Karnak, for example, the main axis is aligned so that the sun rises straight down the central corridor at the winter solstice. Scholars who study Egyptian architecture have measured these orientations with modern instruments. They find that many temples share similar alignments, clustering around certain solar and stellar events. This suggests that Egyptian builders used the sky as a giant reference grid. To lay out a temple, they would watch the rising sun on particular mornings, mark its direction with poles and strings, and then build the walls along that line. The result is a stone building that remembers a moment in the sky. The precision of these alignments is remarkable. At the Temple of Abu Simbel, built by Ramesses II around 1250 BCE, the inner sanctuary is aligned so that twice a year, on dates near the king's birthday and coronation day, sunlight penetrates deep into the temple and illuminates statues of the gods. This alignment required careful planning and precise measurement of the sun's position over many years. The builders had to account for the slight variations in the sun's rising point throughout the year, and choose dates when the alignment would be most dramatic. Egyptian astronomers also developed methods for determining true north using the stars. By watching a star rise and set over several nights, they could find the midpoint between its rising and setting positions, which points toward the north celestial pole. This method is more accurate than using the sun, which moves along the horizon throughout the year. Once they had established true north, they could orient all other directions from that reference point, creating a consistent system for laying out buildings and cities. The Egyptians also used a method called the meridian transit to find north. They would watch a star as it crossed the highest point in its arc across the sky, the meridian. By marking where this highest point occurred relative to landmarks on the horizon, they could determine the north-south line. This method required careful observation over many nights, but it was more precise than using the sun, which changes position throughout the year. The ability to determine true north accurately was essential for aligning pyramids and temples, which were often oriented with remarkable precision. Some Egyptian texts describe the use of a merket, a sighting instrument made of a plumb line and a horizontal bar. An observer would align the bar with a star, and use the plumb line to ensure the instrument was level. By watching a star cross the meridian and marking its position, they could determine north. This simple tool, combined with patient observation, allowed Egyptian builders to achieve alignments accurate to within a fraction of a degree, remarkable precision for ancient times. Archaeologists have found merket instruments in Egyptian tombs, showing that these tools were important enough to be buried with their owners. Modern researchers have recreated merkets and tested their accuracy. They found that with careful use, an observer could determine north to within about half a degree, which is more than accurate enough for aligning large structures. The Great Pyramid of Giza, for example, is aligned to true north with an error of less than 1/10 of a degree. This level of precision, achieved over 400–500 years ago, demonstrates the skill and dedication of Egyptian astronomers and builders. These alignments were not limited to Egypt and Mesopotamia. In Europe, at places like Stonehenge in England, standing stones line up with the rising and setting points of the sun at solstices. At Newgrange in Ireland, a stone passage tomb more than 5,000 years old, a narrow roof box over the entrance, allows a beam of sunlight to shine along the dark inner corridor, only at sunrise on the winter solstice. For a few minutes each year, the chamber fills with light. For the rest of the year, it remains in shadow. The alignment at Newgrange is so precise that modern researchers have calculated it could not have been achieved by chance. The builders had to understand the sun's yearly motion, know exactly when the winter solstice occurred, and then construct the passage and roof box to capture that specific moment. The roof box itself is a narrow opening, only about 20 centimeters wide and 30 centimeters tall, positioned above the entrance. This small window ensures that only light from the low winter sun can enter, and only when the sun is at its southernmost rising point. Similar alignments appear at other Neolithic sites across Europe. At Maeshowe in Scotland, another passage tomb aligns with the setting sun at the winter solstice. At the passage tomb of Knowth, also in Ireland, researchers have found evidence of alignments with both solar and lunar events. These structures show that ancient people were not just randomly building monuments. They were creating permanent markers of celestial events, turning stone into a kind of calendar that would last for thousands of years. The lunar alignments at Knowth are particularly interesting because the moon's motion is more complex than the sun's. The moon's rising and setting points shift in a cycle that takes about 18.6 years to complete. At the extremes of this cycle, called the major and minor lunar standstills, the moon rises and sets at its northernmost and southernmost points. Some researchers believe that the passage tombs at Knowth were aligned to capture light during these extreme lunar events, showing that Neolithic builders understood the moon's complex motion and could predict these special alignments. The effort required to build these aligned structures was enormous. At Newgrange, the passage is over 19 meters long, built with massive stones weighing several tons each. The roof box had to be positioned with precision to capture only the solstice sunlight. All of this work was done with stone tools, human labor, and careful observation of the sky over many years. The fact that these alignments are so precise suggests that skywatching was not a casual activity but a central concern of these ancient communities, important enough to shape their most significant architectural projects. Radiocarbon dating shows that Newgrange was built around 3200 BCE, making it older than both Stonehenge and the Great Pyramid of Giza. The builders had to observe the sun's motion for many years to know exactly where it would rise on the winter solstice. Then they had to design and construct a passage and roof box that would capture that specific moment. Modern engineers using laser levels and computer models would find this challenging. That Neolithic people achieved it with stone tools and careful observation shows how central sky knowledge was to their worldview, and how skilled they were at translating that knowledge into stone. However, some researchers question whether all Neolithic alignments were intentional. Dr. Clive Ruggles, an archaeoastronomer, points out that while some sites clearly show deliberate sky alignments, others may have alignments that are coincidental, or that served multiple purposes. The challenge is distinguishing between intentional astronomical alignment and structures that happen to align with the sky for other reasons, such as topography or practical considerations. This nuanced view reminds us that ancient people were practical, building structures for many reasons, not all of them astronomical. But when multiple lines of evidence point to intentional alignment, as at Newgrange, the case becomes very strong. In the Americas too, similar sky-aware structures appear. At Chaco Canyon in what is now New Mexico, ancestral Puebloan people built great houses with walls carefully aligned to cardinal directions. On a nearby cliff, a spiral petroglyph shares a wall with thin rock slabs. At midday on summer solstice, a bright dagger of sunlight passes through a gap between the rocks and pierces the spiral. On other key days, the light falls just to one side. Researchers believe this sun dagger marked important points in the solar year. Farther south, in the ancient city of Teotihuacan in central Mexico, the broad Avenue of the Dead and the pyramids along it are tilted about 15 degrees away from true north. This is not a mistake. Studies suggest that this orientation lines up with the rising and setting positions of key stars, and with the movement of the sun on specific days. The city itself became a kind of giant observatory, a place where the pattern of the cosmos was built into the ground. What all of these sites share is a simple idea. If you want to map the sky without telescopes, you can fix the positions of important events in stone. You can build walls and doorways and windows that only light up at certain times. You can place pillars so that a star appears to rise between them only on a special day. Over time, these structures become more than buildings. They become part of a living calendar. You might imagine walking through one of these temples before dawn. The air is cool, torches flicker along the walls, people wait quietly. Then, as the first hint of light touches the horizon, a single star appears in the doorway. It is the same star that appeared last year, and the year before and the year before that. The stone remembers where to look. The people remember what it means. Researchers in the field of archaeoastronomy often caution against overreading alignments. Not every stone circle is a perfect observatory. Sometimes walls are oriented for practical reasons, like topography or defense. But when many structures in the same culture share the same careful sky-aligned patterns, and when written records speak of observations of stars and the sun, a picture begins to form. Ancient civilizations did not only map the sky in their minds, they wrote that map into their cities. From your quiet vantage point in the present, you can think of these stone alignments as the first permanent star charts. They are heavy, slow, and rooted in one place. But they accomplish something telescopes also do. They tell you where to look, and when, to see something cosmic. In the next chapter we will climb down from the temple tops, and walk into rooms filled with clay tablets, bamboo strips and papyrus scrolls, where the sky is mapped not in stone and shadow, but in numbers and names. Chapter 3. Writing the Sky Down. Once humans could fix the positions of stars with stones and buildings, the next step was to fix them with symbols. Writing turned fleeting observations into durable records, and records kept for generations turned skywatching into astronomy. In Mesopotamia, scribes pressed symbols into soft clay tablets using a reed stylus. These wedge-shaped marks, called cuneiform, were used to record everything from grain deliveries to royal decrees. They were also used to record the heavens. Some of the oldest surviving astronomical texts list the rising and setting times of stars for each month, along with omens attached to unusual events. One famous set of texts, called the Enuma Anu Enlil, is a long series of omen collections that link sky events with earthly outcomes. A line might say, in simplified form, if a lunar eclipse happens on this date, then this kind of event will happen in the kingdom. To modern readers this looks like astrology, not science. But to compile such lists, someone still had to be watching carefully. They had to know exactly when eclipses occurred, how often planets changed direction against the stars, and when certain stars rose at dawn. Over time, Babylonian astronomers went beyond listing events. They began to notice repeating patterns. They discovered that eclipses tend to recur in cycles of about 18 years, a period we now call the Saros cycle. They also developed mathematical schemes for predicting the positions of planets along the zodiac. Some of these methods used stepwise arithmetic rules written in tables. Others used geometric ideas like areas under curves. All of this work was done without telescopes. It relied entirely on naked eye observations recorded over centuries. The Saros cycle works because of the relationship between the Moon's orbit around Earth and Earth's orbit around the Sun. After about 18 years and 11 days, the Moon, Earth, and Sun return to roughly the same relative positions, so similar eclipses can occur. However, the cycle is not perfect. Each repetition shifts slightly in location and timing. Babylonian astronomers noticed these patterns and developed methods to predict not just when eclipses might occur, but also their approximate location in the sky and their duration. Babylonian planetary predictions used what modern scholars call zigzag functions and step functions. These were mathematical rules that described how a planet's position changed over time. For example, a planet might move at one speed for part of its orbit, then slow down, then speed up again. Babylonian astronomers broke these motions into segments and created tables showing where the planet would be on specific dates. These tables could be used to predict future positions, allowing priests to know when planets would appear in certain constellations, or when they would be visible in the morning or evening sky. The zigzag function got its name from the way it looked when graphed. A planet's motion would increase for a while, then decrease, creating a zigzag pattern. This mathematical model allowed Babylonian astronomers to predict planetary positions, even though they did not understand the physical reasons for the planets' motions. They did not need to know that planets orbit the Sun, or that Earth also moves. They only needed to recognize the patterns and create mathematical rules that matched the observations. This pragmatic approach to astronomy, focusing on prediction rather than explanation, was remarkably effective. Some Babylonian tablets contain what are essentially computer programs written in cuneiform. These are step-by-step instructions for calculating planetary positions. A scribe could follow these instructions, performing arithmetic operations in sequence, and arrive at a predicted position. This is one of the earliest examples of algorithmic computation, showing that ancient astronomers were not just observers, but also mathematicians, who developed systematic methods for processing astronomical data. The fact that these methods worked, producing predictions accurate enough for practical use, demonstrates the sophistication of Babylonian mathematical astronomy. Modern scholars who have studied these Babylonian computational methods have found that they could predict planetary positions to within a few degrees, which is accurate enough to know when and where a planet would be visible in the sky. Some of these methods used linear interpolation, a technique still used in modern computing. The Babylonians also developed methods for handling periodic functions, mathematical descriptions of repeating patterns. These innovations show that Babylonian astronomy was not just about watching the sky, but about developing mathematical tools to understand and predict what they observed. Dr. Mateo Osundriver, a historian of ancient science, has decoded Babylonian computational tablets that show step-by-step procedures for calculating planetary positions. These procedures are remarkably similar to modern algorithms, with clear instructions for each calculation step. The tablets show that Babylonian astronomers understood that planetary motion was not uniform, but could be described using mathematical rules. This understanding, achieved through centuries of observation and calculation, represents one of the great achievements of ancient science. The fact that these methods worked well enough for practical use demonstrates the sophistication of Babylonian mathematical astronomy. In ancient China, court astronomers played a similar role. Early Chinese records describe guest stars that appeared suddenly in the sky, shone brightly for weeks or months, and then faded away. These were likely supernovae or bright novae, exploding stars that temporarily outshone all others. One such record from the year 1054 describes a bright new star visible in daylight. Today we know this event as the supernova that created the Crab Nebula. Chinese astronomical records also describe comets, eclipses, and the regular motions of the Sun, Moon and planets. They include star charts drawn on silk or carved into stone. One surviving stone chart from the Tang dynasty shows more than 300 stars arranged in familiar patterns, with their positions carefully placed. Recent studies suggest that Chinese astronomers mapped the sky systematically, using a grid based on the celestial equator, a method similar in spirit to the coordinate systems modern astronomers use. Chinese star charts often divided the sky into regions associated with different parts of the imperial court. The area around the North Celestial Pole, which never sets for observers in China, was called the Purple Forbidden Enclosure, and was associated with the emperor. Other regions were associated with different officials and functions. This system helped astronomers organize the sky and remember star positions by linking them to familiar social structures. Chinese astronomers also developed sophisticated instruments for measuring star positions. The armillary sphere, a framework of rings representing circles on the celestial sphere, allowed observers to measure angles between stars and track their motions. Some Chinese armillary spheres were large enough for an observer to stand inside, with sighting tubes mounted on the rings. By aligning these tubes with stars and reading scales marked on the rings, astronomers could measure positions, with precision approaching 1 degree, remarkable accuracy for naked eye observations. The Chinese also developed the gnomon to a high degree of sophistication. Some Chinese gnomons were enormous, standing several meters tall. The larger the gnomon, the longer the shadow, and the easier it is to measure small changes in the sun's position. By carefully marking shadow positions throughout the year, Chinese astronomers could determine the length of the year with great precision. Some records suggest they achieved accuracy to within minutes of the modern value, achieved through patient observation over many years. Historical records from the Tang dynasty describe a gnomon that was 40 Chinese feet tall, about 12 meters. This massive instrument would have cast shadows over 15 meters long at certain times of day. By measuring these long shadows with great care, astronomers could detect tiny changes in the sun's position that would be invisible with smaller instruments. Chinese astronomers used these measurements not just to determine the year's length, but also to create accurate calendars, and to predict solstices and equinoxes. The precision they achieved, matching modern values to within minutes, required decades of careful observation and record-keeping. However, building such large instruments was expensive, and required significant resources. Not all Chinese observatories had gnomons this large. Smaller instruments were more common, and astronomers had to work with the limitations of their tools. This practical constraint meant that different observatories might achieve different levels of precision, depending on their resources. The largest instruments were typically built at imperial observatories, where the emperor's support provided the necessary funding. This connection between astronomy and political power was common in many ancient cultures, where accurate calendars and predictions were seen as signs of divine favor and good governance. Chinese star catalogues were often organized by regions of the sky, with stars grouped into constellations that had both astronomical and cultural significance. Some constellations represented figures from Chinese mythology, while others represented parts of the imperial court or important natural features. This dual function, both practical and symbolic, helped astronomers remember star positions, while also connecting the sky to cultural values. The organization of the sky into meaningful patterns made it easier to learn, remember, and teach the positions of hundreds of stars. In ancient Greece, thinkers took another step. They asked not just where objects were, but why they moved as they did. In the 4th century BCE, the philosopher Eudoxus imagined the sky as a set of nested rotating spheres carrying the stars and planets. A little later, in the 3rd and 2nd centuries BCE, astronomers like Hipparchus, and then Hipparchus's later heir Ptolemy, created star catalogues, listing the positions and brightnesses of hundreds of stars. Hipparchus is often credited with discovering precession, the slow wobble of Earth's axis. By comparing his own observations with older records from Babylon, he noticed that the positions of the equinoxes among the stars had drifted over centuries. This subtle shift happens because Earth's rotational axis traces a slow circle in space, like a spinning top that is not perfectly upright. The full cycle takes about 26,000 years. By noticing this, Hipparchus showed how powerful written records can be. A single person, watching for a few decades, cannot see precession clearly. But generations of written data, compared carefully, reveal it. To create his star catalogue, Hipparchus used a kind of sighting instrument called an armillary sphere, or a simple dioptra. These were not telescopes. They were frameworks of rings and sights that allowed him to measure angles between stars with fair precision. He recorded star positions in a coordinate system based on celestial longitude and latitude, measured in degrees. Ptolemy later expanded and refined this catalogue in his book The Almagest, listing over 1,000 stars. Hipparchus's discovery of precession was revolutionary, because it showed that even the fixed stars were not completely fixed. Over long periods their positions shifted very slowly. This meant that star catalogues needed to include not just positions, but also the date when those positions were measured. Future observers could then calculate how much the positions had shifted due to precession. This understanding transformed astronomy from a static mapping exercise into a dynamic science that could track changes over centuries. Ptolemy's Almagest became one of the most influential astronomy books ever written. It not only listed star positions but also described mathematical models for predicting planetary motions. Ptolemy used a system of circles and epicycles, smaller circles moving on larger circles, to explain why planets sometimes appear to move backward against the stars, a phenomenon called retrograde motion. While his models were not physically accurate in the way we understand planetary motion today, they were remarkably good at predicting where planets would appear in the sky. This predictive power made the Almagest the standard astronomy text for over 1,000 years. The Almagest also included detailed instructions for using various instruments, including the armillary sphere, the dioptra and the quadrant. These instructions allowed later astronomers to replicate Ptolemy's observations and verify his results. The book was so comprehensive that it served as both a textbook and a reference work, teaching the methods of astronomy while also providing the data needed for calculations. Its influence extended far beyond the Greek world, being translated into Arabic, Latin and other languages, and remaining the standard astronomy reference until the Renaissance. Ptolemy's star catalogue in the Almagest listed 1022 stars, each with its position in celestial coordinates, and its brightness on a scale from 1 to 6, with 1 being the brightest. This magnitude system, though refined over the centuries, is still used today. The catalogue was organized by constellation, making it easy to find specific stars. Ptolemy also described the shapes and boundaries of 48 constellations, many of which are still recognized today. This systematic organization of the sky into named patterns made it much easier to communicate about star positions and to remember where specific stars were located. Modern astronomers who have compared Ptolemy's star positions with modern measurements have found that most are accurate to within about 1 degree. This level of precision, achieved with naked eye observations and simple instruments, is remarkable. Some stars show larger errors, which may be due to mistakes in copying or to changes in the stars themselves over the past 2,000 years. But the overall accuracy of the catalogue demonstrates how skilled ancient observers were at measuring angles, and how effectively they could record and preserve that information. The fact that we can still use Ptolemy's constellation boundaries today shows how well his system worked. However, recent research by historian of astronomy Dr. Dennis Duke has revealed that Ptolemy may have borrowed many of his star positions from Hipparchus, rather than making all new observations himself. This does not diminish Ptolemy's achievement, as he still organized and refined the data, but it shows how astronomical knowledge was built incrementally, with each generation adding to and improving on the work of their predecessors. The Almagest was not created in isolation, but was part of a long tradition of observation and record-keeping that stretched back centuries. This collaborative, cumulative nature of ancient astronomy is one of its most important features. In the Greek world, constellations took on names and shapes that are still used today: Orion the hunter, Scorpius the scorpion, Leo the lion. These figures were not just decorations, they were organizing tools. Instead of memorizing the exact position of every single star, you could group them into patterns. Once you know the pattern, you can describe the position of a new star as just above the shoulder of Orion, or near the tail of the scorpion. In ancient India, scholars developed their own sky traditions. Texts called the Vedanga Jyotisha, dating back more than 2,000 years, describe the positions of stars, the timing of solstices and equinoxes, and rules for creating calendars. Indian astronomers divided the sky into 27 or 28 lunar mansions, called nakshatras, each marked by a prominent star or star group. As the moon moved across the sky, it passed through these mansions, spending about one night in each. This system allowed careful tracking of lunar motion and helped with ritual timing. Similarly, in the Islamic world centuries later, scholars preserved and expanded Greek and Indian astronomy. In cities like Baghdad, Damascus, and Samarkand, astronomers built observatories with large sighting instruments. They refined star catalogues, improved models of planetary motion, and developed trigonometry to handle spherical geometry on the sky. Once again, no telescopes were involved. Measurements were made with sighting tubes, angular scales, and careful timing of transits. Across all of these cultures, one theme repeats. When you write the sky down, you are no longer limited to what one pair of eyes can see in one lifetime. You can notice slow changes, you can discover cycles. You can compare predictions with reality and adjust your methods. This is how naked-eye stargazing slowly becomes mathematical astronomy. From your resting place now, you can think about all of these clay tablets, bamboo strips, papyrus scrolls, and parchment pages as layers of a single shared notebook. Each mark represents someone looking up, squinting at a star, and deciding to care enough to record it. Over thousands of years, those tiny decisions added up to detailed maps of the sky. complete with coordinates, brightness scales, and catalogs that could be copied and shared. In the next chapter, we will leave the observatories and libraries for a while and head out over open water. Because some of the most impressive star maps ever made were not drawn on paper or carved in stone. They were carried in the minds of navigators who sailed by the night. Chapter 4: Sailing by the Stars. Close your eyes for a moment and imagine yourself standing on the deck of a small canoe far out at sea. There is no land in sight. The water is black and silver, catching the faint light of the stars. The ocean swells beneath you, and the only fixed things are the sky above, and the steady rhythm of your own breath. For thousands of years, people crossed open oceans without compasses, GPS, or maps printed on paper. Instead, they navigated by reading the sky, the waves, and the wind. In the Pacific, master navigators from Polynesian cultures developed an extraordinarily rich star knowledge. They knew which stars rose and set where, which constellations crossed the zenith, and how the sky changed with latitude. Anthropologists who have studied traditional wayfinding, such as the work with navigators from the Caroline Islands, describe how these sailors memorize star paths. A star path is a sequence of stars that rise one after another along the horizon as you move in a particular direction. If you want to sail east, you might watch for a certain star to rise at a certain angle. As the night goes on and that star climbs higher, another star takes its place at the rising point. By following these patterns, navigators can maintain a steady course, even when clouds block parts of the sky for a while. These star paths are often taught through stories and songs. Young apprentices listen as elders recite the names of stars in order, linking each to a direction or a place. In this way, a mental star compass is built, with certain key stars marking the cardinal and intercardinal directions. Unlike a modern magnetic compass with a simple needle, this compass is a network of relationships. This star marks north when it is here, that one marks south when it is there. Research on traditional navigation in Micronesia has found that navigators also pay attention to the height of stars above the horizon. As you travel north or south on Earth, the whole sky seems to tilt. Stars that were low on the horizon rise higher or sink lower. The height of the star Polaris above the northern horizon, for example, gives a good estimate of your latitude in the northern hemisphere. Ancient Greek and Arab sailors used this fact. But even in the southern hemisphere, where there is no bright pole star, navigators can judge their latitude by how high certain familiar constellations climb. Polynesian navigators developed sophisticated methods for estimating latitude using star heights. They would hold their hand at arm's length and count how many finger widths a star was above the horizon. Each finger width represents roughly 1 degree. By memorizing the star heights for different islands, navigators could tell when they had reached the correct latitude. They would then sail east or west along that latitude line until they reached their destination. This method, called latitude sailing, was used by many ancient mariners and remained common until the development of accurate timepieces allowed longitude to be determined. In the southern hemisphere, where Polaris is not visible, navigators use other methods. The Southern Cross constellation, a small but distinctive group of stars, can be used to find the south celestial pole. By extending an imaginary line through the long axis of the cross, navigators can locate the approximate position of the pole, even though no bright star marks it directly. The height of this imaginary point above the horizon gives latitude, just as Polaris does in the north. Some Pacific navigators also use the star Canopus, the second brightest star in the night sky, which passes nearly overhead for observers in parts of the southern Pacific, as a latitude marker. The Southern Cross method requires knowing the relationship between the cross and the pole. The long axis of the cross points roughly toward the pole, but not exactly. Navigators learn to extend this line about 4.5 times the length of the cross to find the pole's approximate position. They also use the two bright stars Alpha and Beta Centauri, which point toward the cross, as additional reference points. This system of relationships between stars creates a mental map that allows navigators to find south, even when the pole itself is not marked by a bright star. Some Pacific navigators also use the star Achernar, which is close to the south celestial pole, though not as close as Polaris is to the North Pole. By watching how high Achernar rises above the horizon, navigators can estimate their latitude. The exact method varies between different island groups, with each developing their own techniques based on which stars are most visible from their location. This local adaptation of navigation methods shows how star knowledge was tailored to specific environments, making it both practical and deeply connected to place. Researchers studying traditional navigation have found that different Pacific Island groups developed different star compasses based on their location. Navigators from the Caroline Islands, for example, use a 32-point star compass, with stars marking not just the 4 cardinal directions, but also many intermediate points. This system allows for very precise course keeping. Navigators from other regions use simpler systems with fewer reference stars. The variation shows how each community adapted star knowledge to their specific needs, and to the stars visible from their latitude. This local adaptation made the navigation systems more practical and easier to learn for people in each region. Anthropologist Dr. David Lewis, who sailed with traditional navigators in the 1960s, documented that these systems were not just memorized, but deeply understood. Navigators could explain why certain stars were used for certain directions, and how the system would change at different latitudes. This understanding allowed them to adapt their methods when traveling to new areas, showing that traditional navigation was not rigid, but flexible and intelligent. The fact that these methods worked reliably across thousands of kilometers of open ocean demonstrates their effectiveness and the skill of the navigators who used them. In the Indian Ocean and Mediterranean, ancient sailors watched stars in similar ways. Greek texts describe how mariners steered by the rising and setting of constellations like Ursa Major and Orion. Arab navigators in the Red Sea and the Indian Ocean developed star tables that listed which stars rose and set at which bearings for different ports. These tables, combined with practical experience, allowed them to sail long routes reliably. On land, desert travelers did the same. In the Sahara and Arabian deserts, caravans moved at night to avoid heat. Guides learned the positions of stars so well that they could steer by them across empty sand. Some Bedouin traditions describe roads of the sky, paths traced by the motion of certain stars overhead. At night, walking beneath a clear Milky Way, those paths gave direction and comfort. In the far north, indigenous peoples such as the Inuit faced a different kind of navigation problem. The landscape of ice and snow can shift and change. In some seasons, the sun barely sets or barely rises, yet the stars, when visible, still provide anchors. Star lore from Arctic cultures includes knowledge of specific constellations used for orientation, as well as careful watching of the moon and planets. What all of these navigators share is an internal star map. It is not a flat chart, it is three-dimensional and dynamic. It includes not only positions but times, when a star first rises, when it crosses the meridian overhead, when it sets, and how those times change with the seasons. That mental map is updated constantly as they travel, comparing expectation with what they actually see. modern researchers have tested the accuracy of traditional wayfinding. In the 1970s, a Polynesian navigator named Mau Piai Lug guided the canoe Hokulea from Hawaii to Tahiti, using only traditional methods, no instruments. He steered by stars, swells, and birds. When scientists later compared his estimated course with modern charts, they found that his mental map of the Pacific matched reality with remarkable precision. Mau Piai Lug's navigation relied on multiple techniques working together. During the day, he watched the sun's position and the direction of ocean swells, which can maintain their direction for hundreds of kilometers. At night, he used star paths, watching which stars rose and set along the horizon. He also paid attention to birds. Certain seabirds fly out to sea in the morning, to feed and return to land in the evening. By watching the direction birds flew, Mau could estimate the direction to the nearest land, even when it was too far away to see. The voyage of the Hokulea demonstrated that traditional navigation was not just legend or luck. It was a sophisticated system that could reliably guide voyagers across thousands of kilometers of open ocean. Since that first voyage, the Hokulea has made many more journeys using traditional methods, helping to revive interest in Polynesian navigation, and proving that these ancient techniques remain viable even in the modern world. The success of these voyages has inspired new generations to learn traditional wayfinding, ensuring that this knowledge continues to be passed down. The training of a traditional navigator is a long process, often taking years or even decades. Apprentices learn not just star positions, but also how to read ocean swells, cloud formations, bird behavior, and other natural signs. They practice by making shorter voyages first, gradually building up to longer journeys. The knowledge is passed down through oral tradition, with elders teaching younger navigators through stories, songs, and direct experience. This method of teaching ensures that the knowledge is not just memorized but deeply understood, becoming part of the navigator's intuitive sense of the ocean and sky. Modern researchers working with traditional navigators have found that their mental maps are incredibly detailed. A navigator might know the star paths for dozens of different routes, each with its own sequence of rising and setting stars. They can also estimate their position by dead reckoning, keeping track of their speed and direction over time. This combination of star navigation, natural signs, and dead reckoning creates a robust system that can work even when some information is unavailable, such as when clouds block the stars, or when ocean conditions make swell reading difficult. Anthropologists who have studied traditional navigation estimate that a master navigator might memorize the positions and motions of 200 or more stars, along with their relationships to each other and to specific routes. This knowledge is not just memorized but deeply understood, allowing navigators to adapt when conditions change. For example, if clouds block the primary navigation star, a navigator can switch to a backup star or use other techniques. This flexibility, combined with the depth of knowledge, makes traditional navigation remarkably reliable. Modern GPS might be more precise, but traditional methods have the advantage of not depending on technology that can fail. However, it is important to note that traditional navigation was not infallible. Historical records and oral traditions mention voyages that went wrong, sometimes with tragic results. The skill required years of training, and not everyone achieved mastery. Some navigators were more skilled than others, and even the best could make mistakes, especially in difficult conditions. This realistic view reminds us that traditional navigation was a human skill, subject to human limitations, even as it achieved remarkable successes. The revival of traditional navigation in recent decades has shown that these methods can still work, but it has also highlighted how much knowledge was lost when modern navigation methods replaced traditional ones. All of this was achieved without telescopes or written maps. The sky itself, combined with human memory and teaching, was enough. The stars became a kind of living grid, painted on the inside of the navigator's mind. As you rest and listen, you might picture those navigators lying in their canoes at night, gazing up, rehearsing the sky the way a musician rehearses a song. Each bright point has a name, a direction, a time of rising. Together those points form not only constellations but routes, a mesh of invisible lines stretching over the ocean. In the next chapter, we will turn from navigation to timekeeping, and see how ancient civilizations used the sky not only to find their way in space, but to find their way in time. Chapter 5: Timekeepers of the Heavens. If you had no watches, no digital clocks and no printed calendars, how would you know what day it is? How would you know when to plant crops, when to harvest, when to hold important festivals? For most of history the answer was simple: you would look up. The sun's daily path across the sky, the changing length of shadows, the tilt of its rising and setting points on the horizon, the phases of the moon, and the appearance and disappearance of certain stars, all serve as natural clocks and calendars. Ancient civilizations turned these repeating patterns into systems of timekeeping with surprising sophistication. One of the simplest tools is the gnomon, a vertical stick or pillar that casts a shadow. As the sun moves, the shadow swings and changes length. By marking the tip of the shadow at noon each day, ancient observers could see the yearly cycle. At summer solstice, the noon shadow is shortest because the sun climbs highest in the sky. At winter solstice, the noon shadow is longest. At the equinoxes, the sun rises exactly due east and sets due west, and day and night are roughly equal in length. In ancient China, Egypt, and Mesopotamia, gnomons were used to determine cardinal directions and to track the solar year. In some cultures, large obelisks or stone pillars doubled as giant gnomons in temple courtyards. Observers would mark shadow positions on the ground, creating what was essentially a large sundial. Over many years, these measurements refined the length of the year to within a small fraction of a day. The Egyptians developed a civil calendar of 365 days, divided into 12 months of 30 days, plus 5 extra days at the end of the year. They noticed that this calendar drifted slowly over centuries compared to the heliacal rising of Sirius and the actual Nile flood, because the true solar year is about 365.25 days. Later civilizations, like the ancient Romans, adjusted their calendars with leap days to keep dates in sync with the seasons. The Maya of Mesoamerica created some of the most intricate calendar systems on Earth, combining several cycles. One 260-day ritual calendar, another 365-day solar calendar, and longer long-count cycles that stretched over thousands of years. They tracked the motions of the Sun, the Moon, and Venus with remarkable precision. Some surviving codices show tables predicting Venus's appearances and disappearances in the sky over long periods, all from naked eye observation. The Maya 260-day calendar, called the Tzolk'in, combines 20-day names with 13 numbers, creating 260 unique combinations before the cycle repeats. This calendar has no obvious astronomical basis, but it may be related to the human gestation period or to agricultural cycles. The 365-day solar calendar, called the Hab, divides the year into 18 months of 20 days each, plus a short month of 5 days. When these two calendars are combined, they create a cycle of 980 days, about 52 years, before the same combination of dates repeats. The Maya were particularly interested in Venus, which they associated with warfare and important events. They tracked Venus's 584-day synodic period, the time it takes for Venus to return to the same position relative to the Sun as seen from Earth. This period includes times when Venus is visible as the morning star, times when it disappears behind the Sun, times when it appears as the evening star, and times when it disappears again. The Maya created tables predicting these appearances and disappearances with accuracy to within a day or two, remarkable precision for naked eye observations over such long periods. The Dresden Codex, one of the few surviving Maya books, contains detailed Venus tables that predict the planet's appearances and disappearances over many cycles. These tables show that Maya astronomers understood that Venus's motion was not perfectly regular. They accounted for small variations in the synodic period, creating correction factors that improved the accuracy of their predictions. This level of sophistication shows that Maya astronomy was not just ritual observation, but a serious attempt to understand and predict celestial motions with mathematical precision. Scholars who have analyzed the Dresden Codex Venus tables have found that they can predict Venus's appearances to within a day or two over periods of hundreds of years. The tables account for the fact that Venus's synodic period varies slightly, ranging from about 580 to 588 days. The Maya astronomers noticed this variation and created correction factors that adjust the predictions accordingly. This attention to detail, combined with the mathematical methods used to create the tables, shows that Maya astronomy was highly developed. The fact that these predictions were accurate enough for practical use demonstrates the skill of Maya observers and their dedication to understanding celestial motions. Maya epigrapher Drive John Carlson has studied the Dresden Codex in detail and found that the Venus tables are part of a larger system that also tracks the Moon, the Sun, and eclipses. The Codex shows that Maya astronomers understood the relationships between different celestial cycles and could predict complex events, like eclipses that depend on multiple cycles aligning. This integrated approach to astronomy, where different celestial bodies were studied together rather than in isolation, shows a sophisticated understanding of the sky. The Maya were not just tracking individual objects but understanding the sky as a system, a perspective that modern astronomy has only fully developed in recent centuries. The Maya also tracked the Moon's motion with great care. They understood the relationship between the synodic month, the time from one new moon to the next, and the sidereal month, the time for the Moon to complete one orbit around Earth. Their lunar tables account for the fact that these periods are slightly different, allowing them to predict lunar phases and eclipses with accuracy. Some Maya inscriptions record eclipse events, showing that they could both predict and observe these dramatic celestial events, integrating them into their complex calendar and ritual systems. The Moon provided another powerful clock. Its phases follow a cycle of about 29.5 days. Many early calendars, from Babylon to China to the Islamic world, were lunar or lunisolar, meaning they tracked months by the Moon but adjusted them with respect to the solar year. Priests and astronomers would watch for the first thin crescent of the new moon in the western sky after sunset, signaling the start of a new month. Because the lunar month does not divide evenly into the solar year, societies develop different ways to reconcile the two. Ancient Babylonians, for example, used a pattern of adding extra months in certain years to keep lunar months in line with the seasons. This practice, called intercalation, was guided by repeated observation of solstices, equinoxes, and star risings. The problem is mathematical. 12 lunar months total about 354 days, which is 11 days shorter than the solar year. If you simply use 12 months per year, the calendar drifts backward through the seasons. After 3 years, you would be off by about a month. After 33 years, you would be off by a full year. To fix this, ancient astronomers developed rules for when to add an extra month. The Babylonians used a 19-year cycle, called the Metonic cycle, after the Greek astronomer Meton, who also described it. In this cycle, 7 extra months are added over 19 years, keeping the lunar and solar calendars roughly in sync. Different cultures developed different intercalation rules. The Jewish calendar uses a similar 19-year cycle. The Islamic calendar, by contrast, does not intercalate at all, which is why Islamic months drift through the seasons. The Chinese calendar uses a more complex system that considers both solar and lunar cycles, adding months when needed to keep festivals aligned with seasons. All of these systems required careful observation of the sky to know when to add the extra time, making accurate star and sun watching essential for maintaining functional calendars. The Chinese calendar system is particularly sophisticated because it tries to reconcile 3 different cycles: the solar year, the lunar month, and a 60-day cycle used for dating. The system adds intercalary months in a pattern that repeats every 19 years, similar to the Metonic cycle, but also adjusts for the fact that the solar year is not exactly 365.25 days. This creates a calendar that stays in sync with both the sun and the moon, though it requires complex rules to determine when to add the extra month. The Chinese system has been refined over thousands of years, with adjustments made periodically to keep it accurate. Historical records show that Chinese calendar reforms occurred regularly, with astronomers adjusting the system to account for accumulated errors. Some of these reforms were major, changing fundamental aspects of how the calendar worked. Others were minor adjustments to intercalation rules or to the length of months. The fact that the calendar needed periodic adjustment shows that Chinese astronomers understood that their measurements were not perfect, and that the calendar would drift over time. This awareness, combined with the willingness to make corrections, kept the Chinese calendar accurate for thousands of years, making it one of the longest continuously used calendar systems in the world. However, calendar reforms were not always purely scientific decisions. Historian of Chinese science Dr. Nathan Sivan has shown that political considerations often influenced when and how calendar reforms were made. A new dynasty might introduce a new calendar to mark a new era, and astronomers had to balance scientific accuracy with political needs. This complexity reminds us that ancient astronomy was embedded in larger social and political systems, not practiced in isolation. The calendar was not just a tool for tracking time, but also a symbol of legitimacy and order, which is why rulers took such interest in its accuracy, and why reforms were sometimes controversial. The Islamic calendar's lack of intercalation means that Islamic months shift about 11 days earlier, each solar year. This means that Ramadan, for example, can occur in any season over a 33-year cycle. While this might seem inconvenient, it has the advantage of simplicity and ensures that all months are treated equally. The calendar is purely lunar, based on actual observations of the new moon crescent, which requires careful sky watching each month to determine when a new month begins. This direct connection to observation keeps the calendar tied to the actual appearance of the moon, even if it drifts relative to the seasons. Stars themselves became markers of time within the year. For example, in ancient Greece and other Mediterranean cultures, the heliacal rising of certain constellations was linked to seasonal activities. The poet Hesiod, writing around the 8th century BCE, advised farmers to begin harvest when the Pleiades rise, and to plough when they set. Astronomers today can use such references to estimate historical dates, because the slow precession of Earth's axis shifts the dates of star risings over centuries. In India, the lunar mansions, the nakshatras, served as a clock for both ritual and agriculture. Each mansion marked a segment of the ecliptic, and the moon's passage through them was used to time ceremonies. Indian astronomers also developed accurate estimates of the length of the year and the synodic month, the time between full moons, again purely through repeated skywatching. What makes all of this so impressive is not just the observational skill, but the patience. To measure the year to within minutes, you need generations of careful notes. To discover that eclipses repeat in cycles, you need to compare many events. To see the slow shift of star positions due to precession, you need to compare present observations with records made long before you were born. The length of the year is not a round number. It is approximately 365.2422 days. To measure this accurately, ancient astronomers had to observe the sun's position relative to the stars or the horizon over many years. They would note when the sun reached its northernmost or southernmost point on the horizon, marking the solstices. By counting the days between solstices over many years and averaging, they could determine the year's length with increasing precision. Some ancient measurements came within minutes of the modern value, achieved through patient observations spanning decades or even centuries. Similarly, discovering eclipse cycles required keeping records of many eclipses and looking for patterns. The Saros cycle of about 18 years was probably discovered by noticing that similar eclipses occurred at roughly regular intervals. But confirming this pattern and refining it required comparing observations across many cycles. Some Babylonian eclipse records span hundreds of years, showing the dedication of ancient astronomers to building up this knowledge slowly, methodically, across generations. The Babylonian eclipse records are remarkable for their detail. They note not just when eclipses occurred but also their type, whether lunar or solar, their duration, and sometimes their magnitude, how much of the sun or moon was covered. This level of detail allowed later astronomers to verify the Saros cycle and to refine eclipse predictions. The records also show that Babylonian astronomers understood that not all eclipses in a Saros series are visible from the same location, because the Earth's rotation and the geometry of the eclipse change slightly with each repetition. Some ancient cultures developed methods for predicting eclipses without understanding their physical cause. The Chinese, for example, used a system based on the relative positions of the sun and moon, calculating when they would align in ways that could produce eclipses. While their methods were not always accurate, they represented a serious attempt to understand and predict these dramatic events. The ability to predict eclipses, even roughly, gave ancient astronomers a powerful tool for demonstrating their knowledge and for timing important events, as eclipses were often seen as significant omens. Chinese eclipse records span over 3,000 years, providing one of the longest continuous records of astronomical observations in the world. These records note not just when eclipses occurred, but also their type, duration, and sometimes their magnitude. Modern astronomers have used these records to study changes in Earth's rotation over time, as the timing of ancient eclipses depends on how fast Earth was spinning. The accuracy of Chinese eclipse predictions improved over time, showing how repeated observation and record-keeping allowed astronomers to refine their methods. By the Tang dynasty, Chinese astronomers could predict eclipses with reasonable accuracy, though they still missed some and predicted others that did not occur. However, some historians caution that Chinese eclipse records may not always be completely reliable. Eclipses were seen as important omens, and there may have been pressure to record them even when they were not fully visible, or to interpret ambiguous events as eclipses. Additionally, some records may have been copied from earlier sources, rather than being direct observations. Despite these limitations, The overall quality and quantity of Chinese eclipse records make them invaluable for modern research. The fact that modern astronomers can use them to study long-term changes in Earth's rotation shows that many of the records are accurate enough for scientific use. You, lying there now and listening, are living at one thin slice of that long chain. But the years and centuries of careful watching by people before you are encoded in our knowledge. When you glance at a digital calendar and trust that the solstice will fall on a particular date, you are quietly relying on thousands of nights of stargazing done by people who had no electronics at all. Ancient timekeeping also had an emotional side. Festivals timed to solstices or star risings marked turning points not just in the seasons, but in people's inner sense of the year. The return of a bright star after weeks of absence felt like a reunion. The longest night of winter, when the sun's path stopped sinking and began to climb again, felt like a promise. In this way, the sky was not only a map and a clock. It was a story of return, of cycles, of endings that are also beginnings. And this sense of cyclical time helped ancient observers stay patient. If you miss a particular eclipse, there will be another in the next cycle. If you cannot measure one heliacal rising perfectly, there will be another chance next year. In the final chapter, we will pull back and think about what all of this means. How did mapping the stars without telescopes change who we are? And what do we still have to learn from those early skywatchers as we drift off to sleep under the same ancient patterns? Chapter 6. What the ancient sky still teaches us. By now you have walked across temple courtyards at dawn, sailed beneath starry skies, stood beside desert caravans, and climbed into high observatories filled with clay tablets and instruments of brass and wood. You have watched people with no telescopes and no electricity map the heavens with nothing but eyes, memory, simple tools and time. So what does all of this add up to? At one level, it is a story about ingenuity. Human beings took the one big canvas available to everyone, the sky, and turned it into a shared reference frame. They found ways to mark directions, to record positions, to predict motions. They turned the apparent chaos of twinkling points into an ordered system of coordinates, cycles and meaning. But at a deeper level, it is a story about patience and attention. Every stone aligned with a solstice sunrise, every star listed on a clay tablet, every navigator reciting a star path on a quiet deck, represents hours of looking and listening. No one person could have built a complete map of the sky alone. It took communities, it took generations. Modern astronomers use telescopes that can see galaxies billions of light-years away, radio waves invisible to our eyes, and X-rays from exploding stars. They measure positions with incredible precision. But even now, much of the basic framework we use, the idea of celestial coordinates, the division of the sky into constellations, the knowledge of precession and cycles of eclipses, has roots in the work of those early observers. When satellites point themselves using star trackers, tiny cameras that recognize star patterns and orient the spacecraft, they are doing a mechanical version of what ancient navigators did with their own eyes. When a space probe uses a star catalog to know where it is pointed, it is leaning on a map whose earliest outlines were drawn by people in robes and sandals, walking temple corridors long ago. Modern star trackers work by taking images of the sky and comparing the patterns of bright stars to a stored catalog. The computer identifies which stars it is seeing, calculates their positions, and determines the spacecraft's orientation. This is essentially what Polynesian navigators did mentally, recognizing star patterns and using them to know their direction. The technology is different, but the fundamental principle is the same. use the fixed patterns of stars as a reference frame for orientation. The star catalogues used by modern spacecraft trace their lineage back to ancient observations. Hipparchus's catalogue, expanded by Ptolemy, was the foundation for later Islamic and European catalogues. These were gradually refined and expanded as telescopes allowed more stars to be measured and positions to be determined with greater precision. But the coordinate systems, the organization of the sky into constellations, and many of the fundamental reference points were established by ancient astronomers working with nothing but their eyes and simple instruments. The continuity of astronomical knowledge across cultures and millennia is remarkable. Greek astronomy was preserved and expanded by Islamic scholars, who then passed it to European astronomers. Chinese astronomy developed independently, but reached similar conclusions about many phenomena. All of these traditions contributed to the foundation of modern astronomy. When we use a star catalogue today, we are using a system that has been refined over thousands of years, but whose basic structure was established by ancient observers who had no telescopes, no computers, and no modern instruments. The constellations we recognize today are mostly from Greek and Roman tradition, but they incorporate elements from even older Babylonian star patterns. The names and stories have changed, but many of the star groupings are the same. This continuity shows how star knowledge was passed down and adapted across cultures. When you look up at Orion tonight, you are seeing the same pattern that ancient Babylonians, Egyptians, Greeks, and many other cultures recognized and named. The stars themselves have moved slightly due to precession, but the pattern remains recognizable, connecting you to observers from thousands of years ago. Archaeologists have found evidence that some constellation patterns are even older than written records. Cave paintings and rock art from tens of thousands of years ago show patterns that might represent star groups. While we cannot be certain, the consistency of certain patterns across widely separated cultures suggests that some basic constellation recognition may be very ancient indeed. The fact that cultures on different continents, with no contact, recognized similar patterns in the same bright stars suggests that these groupings are natural and obvious to human observers. The stories attached to them vary, but the underlying patterns connect us across time and space. However, some researchers caution against overinterpreting ancient art. Dr. Michael Rappengluck, who studies possible astronomical representations in cave art, notes that while some patterns may represent stars, others may have different meanings. The challenge is distinguishing between intentional astronomical representations and patterns that happen to look like star groups. This careful approach reminds us that we must be cautious when interpreting ancient evidence, especially when we cannot ask the creators what they intended. But when multiple lines of evidence support an astronomical interpretation, as with some well-documented examples, the case becomes stronger. There is also a quiet lesson about connection. Standing under a dark sky, ancient people felt themselves part of something larger. The same stars rose over rice fields in China, over pyramids by the Nile, over deserts and forests and islands. Each culture told its own stories about those lights, but the underlying patterns were the same. In that sense, the sky was a shared text that no empire could fully own. Today, light pollution hides much of that text from many of us. But when you do find a dark place and look up, you see what they saw. Orion still climbs the winter sky. The Pleiades still shimmer in a tiny cluster. The Milky Way still spills its hazy band from horizon to horizon. The same slow precession still shifts the sky very slightly each year, marking the passage of ages. If you let yourself relax into that thought, it can feel both humbling and comforting. You are one more observer in a chain that stretches back tens of thousands of years. You are not the first to lie awake under these stars, Wondering how people before you figured out their patterns? You will not be the last. Scientists today still build new instruments and launch new observatories to map the sky in ever greater detail. They measure the positions and motions of billions of stars, trace the structure of our galaxy, and peer into the deep history of the universe. But some of their most precise measurements still begin in simple ways, with an angle, with a time, with the rising of a particular star at a particular point on the horizon. The European Space Agency's Gaia mission, launched in 2013, is creating the most detailed three-dimensional map of our galaxy ever made. It measures the positions, distances, and motions of over 2 billion stars with incredible precision. But even Gaia relies on fundamental concepts developed by ancient astronomers: the idea of celestial coordinates, the division of the sky into reference frames, and the understanding that star positions can be measured and catalogued systematically. The technology is vastly more advanced, but the underlying approach of mapping the sky through careful, repeated observation remains the same. Similarly, when astronomers want to point a telescope at a specific object, they use coordinate systems that have their roots in ancient observations. Right ascension and declination, the modern equivalents of celestial longitude and latitude, are direct descendants of the coordinate systems developed by Hipparchus and Ptolemy. The zero point for these coordinates, the vernal equinox, is still defined by the sun's position relative to the stars, just as ancient astronomers defined it. Even in the age of space telescopes and digital detectors, we are still building on foundations laid thousands of years ago by people who had nothing but their eyes and their patience. The concept of the celestial sphere, an imaginary sphere surrounding Earth with stars fixed on its surface, was developed by ancient Greek astronomers, and is still used today as a convenient reference frame. Even though we know that stars are at vastly different distances, and that Earth moves through space, the celestial sphere remains a useful tool for describing positions and motions. This ancient concept, refined over millennia, continues to be the foundation for how we think about and map the sky. Modern astronomy has also preserved many of the observational techniques developed by ancient astronomers. The method of measuring angles between stars, the use of reference stars for navigation, the tracking of planetary motions against the background of fixed stars, all of these techniques were developed by ancient observers, and remain in use today, though with much more precise instruments. The fundamental approach of careful, repeated observation, recording what you see, looking for patterns, and using those patterns to make predictions, is the same whether you are using your eyes or a space telescope. The tools have changed, but the method remains. Even the most advanced modern telescopes still use coordinate systems based on the celestial sphere concept developed by ancient Greek astronomers. When astronomers point the James Webb Space Telescope at a distant galaxy, they use right ascension and declination, coordinates that trace their origins to Hipparchus and Ptolemy. The zero point for these coordinates, the vernal equinox, is still defined the same way ancient astronomers defined it, by the sun's position relative to the stars. Modern measurements are vastly more precise, but the fundamental framework remains the same. This continuity shows how solid the foundations laid by ancient astronomers were, and how their work continues to shape how we explore the universe today. However, modern astronomy has also moved beyond ancient frameworks in important ways. We now know that stars are at vastly different distances, not fixed on a sphere. We understand that Earth moves through space, not sitting at the center of everything. But the celestial sphere remains a useful reference frame, because it describes how the sky appears from Earth, which is still how we observe it. This practical approach, using a model that is not physically accurate, but is observationally useful, shows how ancient and modern astronomy share a pragmatic approach to understanding the sky. The goal is not perfect models, but useful tools for observation and prediction. So as you drift towards sleep, you might imagine building your own tiny observatory. Maybe it is just a window you always look out of at the same time each night. Maybe it is a tree on the horizon you line a star up with. Maybe it is a favorite spot on a hill. Over weeks and months, you could watch how the sky changes, just as ancient observers did. Slowly, gently, you would begin to feel the sky not as a flat picture, but as a moving, living map. And perhaps, if you let your thoughts stretch just a bit farther, you might feel a kinship with those long-ago skywatchers. The Babylonian priest on a ziggurat, the Egyptian architect sighting along a corridor, the Chinese court astronomer carving a star chart into stone, the Polynesian navigator whispering star names to a young apprentice, the farmer in Greece watching the first appearance of the Pleiades and deciding it is time to harvest. All of them looked up. All of them trusted their eyes and their patience. All of them helped turn the night from a mystery into a map. You live in a time of space telescopes, planetary probes, and star catalogs so large that no human can memorize them. But the simple act that started it all is still available to you. You can step outside, let your eyes adjust, and just watch. You can notice where a bright star rises, how it moves, when it returns. You can let those slow patterns soak into you the way waves soak into sand. Tonight, as you rest, the planets will continue their slow dance against the background of stars. The Earth will carry you gently eastward, making the sky seem to rise in the east and set in the west. Somewhere, on a quiet island, a navigator may still be watching for a familiar star on the horizon. Somewhere, in a high observatory, a detector will tick as a distant photon from a galaxy far away arrives after billions of years of travel. You do not have to track any of this. You can simply let it happen around you. Your breathing can slow, your muscles can soften. The stories of stone temples and star charts can blur into dreams. The same sky that guided ancient civilizations now turns silently above your home. The same constellations that marked their seasons now wheel past your window. You are part of that long, continuous act of looking up. And as your thoughts grow softer and the details of dates and names drift away, you can hold on to one simple image. Humans, in every age, stepping out into the dark, tilting their heads back, and slowly, patiently, learning to read the stars. You can let that image fade now, the stars dimming gently behind your closed eyes, the ancient observatories, and sailing canoes and temple courtyards growing quiet. The map of the sky is still there, full of tiny lights in fixed, patient patterns. You are safe beneath it, a small warmth under a vast, familiar dome. And as you drift into sleep, the stars keep their places, just as they did for our oldest ancestors, waiting for the next pair of eyes to look up and trace their ancient, shining map. The story of how humans mapped the stars without telescopes is really a story about attention and patience. It is about people who spent their lives looking up, noticing small changes, remembering patterns, and passing that knowledge down through generations. It is about communities that work together to build observatories and create calendars, turning individual observations into shared knowledge. And it is about the human ability to find order in what might seem like chaos, to see patterns in thousands of twinkling points, and to use those patterns to navigate, to time, to understand. Tonight, as you rest, you are part of that same long tradition. The stars above you are the same stars that guided ancient navigators across oceans, that marked seasons for farmers, that inspired priests and astronomers to build temples and observatories. The patterns are the same, the motions are the same, the wonder is the same. You may have modern tools and knowledge that ancient skywatchers could not have imagined, but the fundamental experience of looking up at a dark sky full of stars connects you to every human who has ever done the same. So let your thoughts drift now, from ancient ziggurats to modern space probes, from stone circles to digital star catalogues, from the first person who noticed that a star always rose before the flood, to the latest measurements from orbiting telescopes. All of it is part of one continuous story, one long effort to understand the sky and our place within it. The methods have changed, the precision has increased, but the basic human impulse to look up and wonder remains the same. The stars will still be there when you wake, patient and steady, just as they have been for all of human history. And somewhere, someone else will be looking up, learning the patterns, beginning their own journey of mapping the sky. The tradition continues, one observer at a time, one clear night at a time, building on all the knowledge that came before, adding their own small observations to the vast shared map of the heavens. Sleep well, knowing that you are part of this long, beautiful story of humans and stars, of eyes looking up and minds trying to understand, of patience and wonder stretching across thousands of years. The map is still being drawn, and you are part of it.